Hello guys, welcome back to my channel. And in this rather notable video, I would actually like to solve the Bessel problem, or the infinite series of 1 over n squared, the inverse squares infinite series. And before just starting with this rather elementary proof, I would like to point out two things. First of all is, I will not take credit for this elementary and elegant method of proving or solving the Bessel problem, because it's actually from a book, and it's being used by a bunch of people who post math problems on Instagram. So I take no credit for this proof. And secondly, the more popular version of solving the Bessel problem is by using Fourier series, and that will be another video entirely. Okay, so with that being said, let's get started. Okay, so before starting, I just wanted to write what the problem actually was. So call that S. It's defined as the infinite sum from n equals 1 to infinity of 1 over n squared, and it turns out this converges. So we can actually assign a finite value for this convergent sum. Okay, so with that being said, we're actually going to start with something that may seem a little off track, but stuff will just elegantly transform. So we start with this integral I, which we define to be integral from 0 to 1 of dx over 1 plus ax times square root of 1 minus x squared, and a is just some random constant. I mean, in case you're wondering, this is what I call elementary. This on this channel, elementary is in the form of an integral. So elementary is equal to integral. I mean, at least that's still better than the Fourier series, right? Because I don't know, I'm assuming most of you don't know Fourier series, or you would have to recap about Fourier series. So anyways, let's actually try to simplify this. So noticing the square root of 1 minus x squared, it is actually of a standard form, and it beckons us to use this substitution. X is equal to sine theta. That's because dx is equal to cosine theta d theta. So I will become integral from 0 to pi over 2. You can work out the upper and lower bounds. Dx is cosine theta d theta over 1 plus a times sine theta, and then square root of 1 minus sine squared theta is cosine theta. And that's exactly why we use this substitution, because notice how the cosine thetas will cancel out, just giving us integral from 0 to pi over 2 of d theta over 1 plus a times sine theta. And noticing sines or trigonometric terms in the denominator having power 1, now would be a good time to implement the Weierstrass substitution. And those of you who aren't formally trained with calling the tan half angle formula something else, know that the Weierstrass substitution is actually the same as the tan half angle method. I mean, I just learned about calling the tan half angle method the Weierstrass substitution like last year or something. So okay, so with that being said, we can actually perform a substitution, And well, before a substitution, let's convert everything into half angle formulas for tangents. So this sine will become 2a tan theta by 2 divided by 1 plus tan squared theta by 2. So you can take a common denominator. 1 plus tan squared theta by 2 will become secant squared theta by 2 d theta divided by 1 plus tan squared theta by 2 plus 2a tan theta by 2. Fair enough. Okay, now it's actually time to use substitution, because it's very clever, that it's very evident that the derivative of tan theta by 2 is basically secant squared theta by 2, along with some factors of 2 or a half. We'll figure that out. So let y equal tan theta by 2 such that dy is secant squared theta by 2 with a half because of the chain rule d theta. So the numerator is effectively 2 dy, and the upper and lower bounds, well, you can plug them in. So for 0 you have tan of 0, which is 0. For pi over 2 we have tan of pi over 2 over 2, tan of pi over 4, which is 1. So you have 2 dy, as we figured out over here, 1 plus y squared plus 2ay. Now what I'm going to do is, just like you have a quadratic in the denominator and you're finding the antiderivative of that, same method as that, you try to complete the square. So when we do that, we can write the denominator as y squared plus 2ay plus 1, plus a squared, but you'll have to subtract a squared from the 1, because a squared wasn't there originally, there was a 1. So adding and subtracting a squared. Noticing now that this first term is just y plus a, but the whole thing squared, and the second term can be expressed as a square too. Square root of 1 minus a squared, but the whole thing square. So the square and the root cancel out. Okay, now this is actually this actually resembles something. That's right, it's actually the formula, one of the formulas of the inverse tangents in the antiderivative list. I will be making a video on integral calculus in my high school calculus playlist, but I think there's like a still a pretty significant amount of time before I do that and prove these formulas one by one. So if inverse tangent of y plus a over square root of 1 minus a squared, evaluated from 0 to 1. Okay, so evaluating this now carefully, we have inverse tangent of 1 plus a over square root of 1 minus a squared minus inverse tangent of a over square root of 1 minus a squared. And now isn't this fabulous, because we have a difference of inverse tangents and we actually have a formula for that. So note that the inverse tangent of a plus, rather minus the inverse tangent of b in this case, let's deal with the negative first, is equal to inverse tangent of a minus b over 1 plus a times b. So we have this formula here. I will do a proof of this once I make an entire video on inverse trigonometric function. So we have 2 over 1 minus a squared under square root, and then this will become inverse tangent of 1 plus a over square root of 1 minus a squared minus a over square root of 1 minus a squared, but still all of this is divided by 1 plus a times 1 plus a, and then we have square root of 1 minus a squared whole thing squared, which is 1 minus a squared, like that. And don't worry, this will seem ugly at first, but we can actually reduce it down. So notice the a's will cancel out. You have 1 over square root of 1 minus a squared divided by, you'll have 1 minus a squared plus a squared divided by 1 minus a squared. So the a squares will cancel out. We have 2 over square root of 1 minus a squared inverse tangent of, well, this will cancel out with one of these because this is square root square. So this will go in the numerator then. So square root of 1 minus a squared divided by, well, 1 plus a. That's I. Okay, and being true mathematicians, we aren't satisfied with this still, because we notice the 2 up front, and we also recall the duplication formula for the inverse tangent. So again, note that 2 times inverse tangent of some angle C is equal to inverse tangent of 2c over 1 minus c squared. So again, implementing that, we have 2, we lose the 2, so we have a 1 over 1 minus a squared, and then inverse tangent of 2 times square root of 1 minus a squared over 1 plus a divided by 1 minus this entire term squared, which will be 1 minus a squared over 1 plus a, but the whole thing squared. And we can simplify this to inverse tangent of, well, it looks like these denominators can simplify a little bit. So we have 2 times square root of 1 minus a squared divided by 1 plus a. All that is still against square of this, which is 1 plus 2a plus a squared minus 1 plus a squared, which is divided by 1 plus a, the whole thing squared. So okay, this cancels with one of this. 1 over square root of 1 minus a squared inverse tangent of 2 times square root of 1 minus a squared 1 plus a over the 1 can cancel out. We'll have a 2a plus 2a squared. So 2 times, or rather 2a times 1 plus a. So 2 cancels, 1 plus a cancels. All we have left is square root of 1 minus a squared under root inverse tangent of square root 1 minus a squared over, well, a. And believe me, I know you won't at this point, that we can simplify this further. We can actually draw up a triangle. So the inverse tangent is some angle alpha. It's a really crooked triangle, but bear with me. This is alpha, inverse tangent. Having an inverse tangent like this, but a tangent is opposite upon adjacent. So if square root of 1 minus a squared were the opposite side and a were the adjacent side, then tan of alpha would actually be the argument of this. Therefore, inverse tangent of this divided by this would be alpha, like we originally defined. We originally defined this expression, this inverse tangent, to be alpha. So take the tan on both sides. So tan alpha is equal to square root of 1 minus a squared over a. And hence we constructed a triangle having these sides. So by the Pythagorean theorem, the hypotenuse will just be a squared plus the square of this, which is 1 minus a squared, giving us 1 over here. And to really simplify stuff, I would like to write I that we started with instead of, well, inverse cosines, because alpha will now be, if you want to use inverse cosines, the adjacent is a, hypotenuse is 1, so a over 1, or just inverse cosine of a. So I is just cos inverse a over square root 1 minus a squared. That's I, and that's actually all about our introductory lemma that we need for this proof. And now, to see this in a new light, I beckon you to join me on a fresh page. See you there. Okay, now we know I turned out to be this. Now we can actually perform another integration. I know this is gamma di gamma. Our elementary is integration, even if it's like integration on another integration. So I'm calling B for the Bessel problem. The integral from negative 1 to 1 of I, but now integrated with respect to A. So just to rewrite, and you'll get a perspective of what's going on. Instead of I, we have integral from 0 to 1 of dx over 1 plus ax square root of 1 minus x squared dA. So suddenly the a that was actually being treated as a constant is actually an important person, so it just got promoted. And guess what? We know what I is. We know what this inside integral is. Integral from negative 1 to 1 of cosine inverse of a over square root of 1 minus a squared dA. So yeah, we know what this is, like, clearly. So to again evaluate this, notice the denominator is of a standard form, so we can use a standard substitution. So noticing the cosine inverse on top, let a equal, I don't know, cosine of some other angle, I don't know what to call it, beta for now. Then dA would be negative sine beta dB, d beta rather. Always confused with the b's, but okay. So B is, well, when is a cosine of some angle negative 1? Well, there are many possibilities, right? But notice that the cosine inverse has a range from 0 to pi, so we have to choose some values that are, actually satisfying this interval, in this interval, that are lying in this interval. Otherwise this substitution would just kind of won't make sense, because you can't invert a function. Again, there are a lot of problems. I'll be discussing them in detail in the inverse trigonometric functions video. So when cosine of pi is negative 1, that's when you'll have negative 1 by this substitution. So when beta is equal to pi, and when will cosine be 1? Well, 0, right? Basically the apex, the apices of this interval, and we'll have a cosine inverse of cosine beta of, well, sine beta, and instead of the dA we have negative sine beta d beta. So these cancel out, We have negative integral from pi to 0. These are inverse functions cancelling out to beta d beta, and this is just simple. This is negative beta squared by 2 by the power rule, evaluated from 0 to pi. So when you plug in 0, you'll have, well, 0 minus, and this minus will make a plus, and when you plug in pi, you'll have pi squared over 2. So b, the Bessel problem integral, is pi squared over 2. Okay, so suck on that for now. Now this was one perspective, right? This was one perspective of looking at b when we were reintegrating I. So there is actually another perspective, and let me go on a fresh page. I'll explain it to you. Okay, so all I've done on this page is just written I, the definition of I, which we calculated to be cosine inverse of a over square root of 1 minus a squared, and then b, that we defined to be integral from -1 to 1 of I dA, which turned out to be this double integral. But plugging in I, cosine inverse of a over square root of 1 minus a squared dA, gave our first perspective, which turned out to be pi squared over 2. Now for our second perspective, what we're going to do is simply interchange these two integrals, and again assuming uniform and absolute convergence, otherwise it wouldn't work. And now this is a very good assumption to make, because we're going from -1 to 1, which is well within the range of the cosine inverse function. Also, these upper and lower bounds, they aren't any improper values like infinities or like zeros, where stuff is just getting blowing up to infinity. So with that in mind, we have integral from 0 to 1 of integral from -1 to 1 of now a dA over 1 plus ax square root of 1 minus x squared dx. And now we're integrating with respect to a, so all the x terms are constants, and this is a linear term basically. Integral from 0 to 1 of, well, antiderivative of this is natural log of 1 plus ax divided by the constant coefficient associated with the variable of integration a, which turned out to be x, times square root of 1 minus x squared. But you still have to evaluate this from a equals -1 to a equals 1 dx. So when I do that, I have integral from 0 to 1 natural log of 1 plus x over x times square root of 1 minus x squared minus natural log of 1 minus x over square root of x times square root of 1 minus x squared dx, and I like to bracket this out. Okay, so what we're going to do is use some log properties, club this up as natural log of 1 plus x over 1 minus x divided by x times square root of 1 minus x squared dx. And now I would like to use some classic substitution, trigonometric substitution. Let x equal, say, cosine of capital R. I'm running out of variable names for angles. So dx is negative sine R dr. So when is cosine 0? At pi over 2. And when is cosine 1? At 0. Take the negative outside. We have natural log of 1 plus cosine R over 1 minus cosine R divided by cosine R square root of 1 minus cosine squared R dx is, we took the negative outside, sine R dr. Now using the negative to correct this order of integration, and then using the half angle formula, we have 2 cosine squared R over 2 divided by 2 sine squared R over 2. We have a cosine R here, and by square identity is a sine R here and a sine R dr on top. So the sine R's will cancel off. Over here we have integral from 0 to pi over 2. Natural log, 2 cancels off. Natural log of cotangent squared r over 2 divided by cosine r dr. I would like actually like to bring the power down from the cosine squared. Using log properties, we have the power down 2. And taking a negative, I would like to take the reciprocal of the cotangent, which is the tangent of r over 2, divided by cosine r dr. And notice we have a half angle here and a full angle here. So again, using half angle formula for the cosine, with natural log of tan r over 2 over 1 minus tan squared r over 2 divided by 1 plus tan squared r over 2, which will go on top, dr. Noticing that this is secant squared r over 2, which is indeed a multiple of the derivative of the tan r over 2. Make a substitution like we did for perspective, rather corollary lemma, introductory lemma. So let w equals tan of r over 2. dw is half secant squared r over 2 dr. So our numerator is effectively 2 dw along with this natural log term. So we have negative 2 times the 2 from this will make it 4. Integral from 0 to 1, you can figure it out on yourself. Natural log of w over 1 minus w squared, and the rest is dw. So now noticing uh, the limits of integration 0 to 1, we can actually use the infinite geometric series, because we have 1 over 1 minus polynomial. So we have negative integral from 0 to 1, sum from say n equals 1 to infinity, w to the 2 raised to n minus 1 power, natural log of w dw, which will make it negative 4. Again, interchanging the sum and integral, assuming convergence. Integral from 0 to 1, w to the 2n minus 2, natural log of w dw. Now I would like to use integration by parts, integrating this, differentiating this while I'm at it. Negative 4, sum from n equals 1 to infinity. We have w to the 2n minus 1, natural log of w, divided by 2n minus 1, evaluated from 0 to 1, minus integral from 0 to 1, w to the 2n minus 1 over 2n minus 1 times 1 over w dw. So when you plug in 1, because of the natural log of 1 being 0, this goes to 0. Plugging in 0, you should ideally use L'Hopital's rule, but noticing that the polynomial is, well, growing faster than the natural log, entire thing will go to 0 again. So we have a negative negative positive 4, sum from n equals 1 to infinity of, we have integral from 0 to 1, w to the 2n minus 2 over 2n minus 1 dw. Now this antiderivative is pretty elementary. W to the 2n minus 1 over 2n minus 1 times 2n minus 1, which is 2n minus 1 squared, evaluated from 0 to 1. At 0, of course, it goes to 0. At 1, the numerator just becomes 1. So 1 over 2n minus 1 squared. And this, if you write out some terms, is the inverse square series, but with like odd numbers. And if you call your original Bessel problem, sum from n equals 1 to infinity 1 over n squared, as S, then this is actually composed of all even terms, which you can represent as 2n the whole thing squared, and all odd terms. Sum from n equals 1 to infinity of 1 over odd terms you'll represent as 2n minus 1 whole thing squared, which is exactly our b over 4. If you isolate this out, you'll have a b over 4. So S is equal to, you can factorize out the 1 over 2 the whole thing squared, which is 1 over 4, sum from n equals 1 to infinity 1 over n squared, plus this will be b over 4, like because of this. This is just s but with a 1 over 4, so s is equal to s over 4 plus b over 4. We have 3s over 4 is equal to b over 4, cancel out the 4. S is actually b over 3, but what is b? From perspective 1, if you remember, b is pi squared over 2. So all we have here is pi squared over 2 along with a factor of 1/3, which turns out to be pi squared over 6. And what is s? Let's write it down officially. Sum from n equals 1 to infinity 1 over n squared. That turned out to be pi squared over 6. So it's truly a magnificent answer. And I think this is it for this video, guys. I hope you learned a lot as much as I did. A really elegant proof. Hats off to the one who actually brewed this. So hey, please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread my word in the math community or wherever you can find people who are interested in this kind of stuff. And in the meantime, stay home, stay safe, keep doing math. And before saying peace out, please stay tuned for more content from this channel. And finally, peace out. Signing off.